a 0.0065 kilogram bullet traveling horizontally with a speed of 1 times 10 to the, I'm going to assume that's third, so 10 to the third, which is 1,000 meters per second. That seems like a reasonable bullet speed. Maybe 3,000 feet per second? Yeah, probably. Strikes a 20 kilogram, that's a pretty hefty door. Embedding itself 11 centimeters from the side opposite the hinge. 11 centimeters from the side opposite the hinges as shown. So I'm going to assume that this is 0.11 meters. I assume that's what they mean. And they don't mean that this distance down here is. Because otherwise they'd have to tell us the whole length of the door. Ah, they do tell us that. Never mind. Never mind. Scratch that. So this is 1 meter total. Whoop, 1 meter total. And this distance right here is 0.11 meters, which means that this distance right here is going to be 0.89 meters. Yeah, that seems reasonable. Okay. Yeah. The doors, wide, 1 meter wide doors, free to swing frictionless on its hinges. Okay. Before it hits the door, does the bullet have angular momentum relative to the door's axis of rotation? Yes. Yes, it does. And the easiest way to view that is momentum equals P equals mv. The angular analog is L. Angular momentum equals I omega. And the relationship between V and omega is, let's see here, X equals R theta, V equals R omega, A equals R alpha. But this really isn't the entire truth here. What this really is the velocity vector is the R vector cross the omega vector. And so the idea here is the velocity goes this way, the R vector is this way, and so when you look at the cross product between those two, you can view, when you view a cross product as a measure of how perpendicular two vectors are, or you can view it as only looking at the perpendicular component of the vectors. So this would be the same as R perpendicular times omega, which would also be the same as R omega perpendicular. What we're going to do with this version right here is what we're going to look at. So what that's saying is, if this is R, this would be R perpendicular. We look at the portion of the radius, the R distance, that is perpendicular to velocity. So that's the concept that we're going for here. And we look at it in that light, and you're like, okay, yes, it does have angular momentum relative to the door's axis. And this is one of the first times when we looked at angular momentum where this cross product right here isn't 1. If so, evaluate this angular momentum. All right, so we're going to use L equals I omega. Now this is a little bit mathematically maybe questionable, but I'm going to use I equals mr squared, which is the moment of inertia for a point charge. But specifically, I'm going to use mr perpendicular. So I'm only going to use the perpendicular value, the perpendicular moment arm. And then I'm going to say that omega equals V over R. And again, I'm going to use only the perpendicular value. And so L, angular momentum, equals mr perpendicular squared times V over R perpendicular. Cancel, cancel. We get mr perpendicular V as our angular momentum. And so this is going to be 0.0065 times our perpendicular distance, which is right here, 0.89, times the speed of the bullet, which we said was 1,000 meters per second. Put that all in, 0.0065 times 0.89 times 1,000, and we get a value of 5.785 and that's going to be kilograms meters squared per second. The only reason I know those units is because it's written right up there. Some units I've memorized, some I don't. So if I was a smarter person, I would. I'm not. So is mechanical energy of the bullet, yep, so that's the answer to number B. Is the mechanical energy of the bullet door system constant in this collision? Answer without doing calculations, no, it is not. And the reason you know that is because of this word right here, embedding. So the bullet embeds itself, which means it's an inelastic collision. Inelastic means like kinetic energy is not conserved because there is deformation of the system. So whenever anything deforms, that takes energy, therefore kinetic energy is lost. If it bullet hit the door, bounced off like a cue ball, then maybe. But that is not what happened. So no. Is mechanical energy conserved? It is not, because some energy is lost to deformation, heat, or something. At what angular speed in radians per second does the door swing open immediately following the collision? All right, so for this is going to be conservation of momentum, just a collision problem. Angular momentum initial equals angular momentum final. Angular momentum bullet initial plus angular momentum door initial equals angular momentum bullet door final. And I put bullet and door together because once it embeds itself, it's just one system. For angular momentum, I'm going to use angular momentum equals I omega. The initial angular speed of the door, when it's just sitting there prior to being hit with a bullet, is 0. So that angular momentum is going to be 0. So I'm going to say moment of inertia bullet times angular speed. No, actually I'm not going to do that because we already found the angular momentum. I'm just going to leave that LB. Angular momentum bullet initial equals moment of inertia bullet door times the angular speed bullet door final. Rearranging this, the angular speed bullet door final equals our initial angular momentum of the bullet divided by the moment of inertia of our bullet door system. There's going to be a little sidebar right here. The moment of inertia bullet door is going to be moment of inertia bullet plus moment of inertia door, which is going to be, for the bullet, it's going to be mr squared. It's just going to be a particle. So I'm going to call it mass bullet radius bullet squared plus, and now for the door, it's going to be a hinged, basically a hinged stick, but it's going to be three-dimensional. So I'm going to look that up. Lists of moment of inertia. Can I do that? Maybe. I'm going to go with this. So I'm going to say that this door is the same as a thin rod rotating about the axis like so. This is a door, that's the hinge, 1/3 ml squared. Yeah, I'm going to go with that, and I'm going to be confident about it. So now I'm going to come back down here, plug that in. So a moment of inertia was 1/3 ml squared, where L is the length of the door. Yep, I'm good with that. So now we're going to come back up here to our equation, put that in, and then we'll plug in some numbers. So moment of inertia, bullet initial, all over m bullet radius bullet squared plus 1/3 mass door, a little d there for door, L squared. Now this is going to give us some values here. So we had angular momentum of the bullet was 5.875, 5.785, all over mass of the bullet, 0.0065. Radius of the bullet, how far it hit from the door, which was 11 centimeters from the end, which is 0.89 meters. 0.89 squared plus 1/3 mass of the door. I think they said 40 kilograms, 20 kilograms. 40 kilograms would be a very heavy door, about 40 pounds. 20 kilograms times the length of the door, which is 1 meter, and we'll square that, though it's 1. So really the square is just there to look pretty, which is valuable in and of itself, I suppose. So 0.0065, make sure that that's the correct mass. 0.0065, yep, it is. Come down here, divide value, 0.0065 times 0.89 squared plus quantity, 1/3, times 20 times 1 squared. And I get a value of, big, good old Wolfram, old faithful, 1.065, mr squared, 1/3, ml squared, 0.867, maybe, equals 0.867, and this is going to be in radians per second. Hopefully that's what they wanted. What's the angular speed? 0.867 radians per second. Door swing open immediately after the collision. Okay. Calculate the total energy of the bullet door system and determine whether it is less than equal to or equal to the kinetic energy of the bullet before the collision. Answer what? Okay. So energy kinetic initial, we're just going to do 1/2 mv squared, where this is all from the bullet. So the bullet is going to have all the energy because the door is not moving. So this is 1/2 mass bullet, velocity bullet squared, which is 1/2 0.0065 times velocity of the bullet, which I think we said was 1,000. 1,000 squared. This gives us an answer of 0.0065, 0.5 times 0.0065 times 1,000 squared. This gives us a huge number of 3250 joules. And now, this would be energy kinetic initial. Now we'll do energy kinetic final, which should be less, because some energy was lost in the embedding deformation process. So we're going to use the same idea, 1/2 mv squared, except we're going to use the angular equivalent, because I think we got more data for that. We could, yeah, this is going to be much easier. 1/2 I omega squared. So this would be 1/2 moment of inertia. We already found right over here. Make it a little bit smaller just for convenience. That is the moment of inertia total of our system times omega final squared, which we now know because we just found it. 1/2 0.0065 times radius of the bullet squared, which is 0.89 squared plus 1/3 times mass of the door, which is 20, times the length of the door, which is 1 squared, times the angular speed, 0.867 squared. And this is going to give us, underline that so I know this, is going to give us an answer, hopefully an answer that is less than 3250. Let's see, how do I want to do this? There we go. This would be 0.5 times 0.867 squared. 1/2 I omega squared. Wow, that's a big drop. Maybe. So this would be 0.5. That's the moment of inertia, and that is the angular speed of the door squared. Now we'll try it, see what happens. And this is 2.51 joules. So much, much smaller. Energy kinetic initial, 3250. This is 2151 joules. Imagine now that the door is hanging vertically downward, hinged at the top so that the figure is a side view of the door, the bullet collision. What is the maximum height in centimeters at the bottom of the door will reach after the collision? Okay, so maximum height at the bottom of the door. So what we're going to say is we have a door hinged like this, and then it's hit, and it swings up like that. Specifically, what we're going to say is that the center of mass of the door gains potential energy of 2.5 joules, not a lot. So we're going to say this is going to be a conservation of energy. So energy kinetic initial plus energy potential initial of the door bullet system equals energy kinetic final plus energy potential final. So I'm going to say that initially it starts at the bottom, so the energy potential is 0. I'm going to say that the kinetic energy final is 0 because when it swings up and comes to a stop, once it comes to a stop, no longer has any motion, therefore kinetic energy 0. From there, I'm going to write this out. 1/2 mv initial squared equals mass, gravity, height. So the masses on both sides cancel, which is convenient. Therefore, height equals v naught squared over 2g. The velocity, v equals r omega. So the velocity of the center of mass. So this is going to be the velocity at the bottom of the door, right there. And that is going to be, I'm just going to figure that out because I can. The radius at the bottom of the door is 1. Actually, no, what I'm going to do is I'm going to find the velocity of the center of mass. So I'm going to do it right there. So the velocity, the radius is going to be 1/2 because the length of the door is 1 meter. Therefore, the center of the mass, we're going to assume, I'm going to neglect the bullet. I know I should probably take into account that the bullet is there, but it's 0.065 and the door is 20 kilograms. Negligible. I know. Mathematically, dubious. It'll work out. More of an engineering than a math thing. 1/2 omega, we found out, was 0.867. 0.867. So the velocity is, do the math, 0.5 times 0.867, 0.4335 meters per second, which is pretty respectable. So then the height is going to be 0.4335 squared over 2 times 9.8. Where I'm going to say 9.8 is gravity. Close enough. Maybe. Possibly. Fair. So we'll do 0.5 times 0.867 squared divided by 2 times 9.8. Not very high. We'll see. So 0.5 times 0.867, which is the speed, squared over 2 times 9.8. And we get an answer of 0.0096, which I'm going to say is 0.01 meters. That's going to be 1 centimeter, and that's the center of mass rises 1 centimeter. Therefore, at the bottom of the door, which is twice as far away, that's going to rise twice as much. And so change in height is going to be 2 centimeters. There was a lot to this problem. So put that in real quick. 2 centimeters, which is convenient because I wanted it in centimeters. So we're going to recap what we did on this problem because there was a lot that went on here. So we had a bullet that shot into a door and it embedded itself. So we had a collision. This is an inelastic collision. We have two things come together and stick. Inelastic collision. So inelastic collisions, the momentum is conserved. All collisions, momentum is always conserved. It's only with so inelastic collision, only elastic collisions preserve kinetic energy. So, or mechanical energy, I guess. Idea, energy is not conserved. So it hits it, we take the angular momentum of the bullet, we add it to the initial angular momentum of the door, which is 0 because it's not initially moving. They hit each other, and they both kind of fly off. And it's going to have a final angular momentum, which we calculate. We find the initial energy, the final energy. So we found the initial energy because it was just from the bullet. We used 1/2 mv squared. Then we find the final energy, which we still use the kinetic energy equation, except now we use I omega squared because we just have the data for that. It's way easier. And we find that almost all the energy is absorbed in deformation. From there, imagine now that the door is hanging vertically, and we found out how high the door would swing, so we drew a little arrow thing. What I did was I found out how high the center of the mass swung. Center of mass, I said, was in the middle. Really, it'd be slightly below the middle because the bullet adds mass and not a uniform door anymore. It's a small bullet, I don't care. And so I said it rose up slightly. We did whole conservation of energy, so how far it swung up. So we found out how far the center of mass of the door swung up. We then had to double that because we're not concerned with how high the maximum height of the door went up, center of mass of the door, but the bottom of the door. And so we wanted to look at how far this was. So this would be 2 centimeters if that was 1 centimeter rise up here. That's 1 centimeter, that's 2 centimeters. So and that's how we went through this problem. It's a bit of work on this one. This one's not easy, I'm not going to lie. So hope that helped though. See you on the next one.